Today I'm asking a specific question. If information is fundamental in physics, when and why does it appear to be lost? Across several fields, the same pattern appears. Information is often present in the physical system, but it may be inaccessible, scrambled, hidden in correlations, or unrecognizable without the right mathematical framework. This presentation begins with Shannon entropy as a measure of uncertainty, moves through thermodynamics, chaos, and quantum mechanics, and then ask how modern AI and machine learning are being used to extract hidden information from DNA, protein structure, gravitational waves, weak lensing, and cosmological data. I will end with black holes and the holographic principle, where the question becomes even deeper. Perhaps information is not stored where we intuitively expect it, but on boundaries or in physical laws themselves. The central claim: information is structured by law, hidden in correlations, and revealed by the right framework. Apparent information loss often reflects the limits of access, recognition, or a framework rather than literal destruction. Apparent information loss can be found in missing pieces, hidden order, practical unrecoverability, correlations, environmental dispersal, unrecognized structures, and boundary encoding. Information looks missing. This is the most basic form of hidden information. The structure exists, but from our limited view, it looks incomplete. Shannon gives us the first mathematical way to talk about that uncertainty. Shannon entropy measures the expected information content of a random variable. If an event is certain, its information content is low, because observing it tells us almost nothing new. If outcomes are evenly distributed, uncertainty is high, and the average information gained from observing an outcome is also high. For a binary variable, the entropy is defined as h of x is equal to the negative summation of the probability p of one of the outcomes times the log 2 of that probability outcome. This gives us a weighted average of the outcomes. And it reaches its maximum at p equals 0.5, where each outcome is equally likely. This is powerful because it turns information into something measurable in bits. But it is also limited. Shannon entropy deliberately ignores meaning. For example, a random DNA sequence and a biological functional DNA sequence may have statistical entropy, even though one carries functional biological structure and the other may not. That limitation is central to my presentation. Information is not just uncertainty. In physical systems, meaningful information is often tied to structure, function, constraints, and correlations. Hidden order is not the same as randomness. For example, a shuffled deck may look random if I do not know the order, but the order still exists physically. This helps introduce entropy as a gap between the full microscopic state and what an observer can actually know. We are often bad at recognizing information when we see it. Imagine two DNA strands of equal length. One is random. The other is part of a functional genome. In a simple Shannon calculation, they may have similar entropy because both have distributions of A, T, C, and G, but biologically they are not equivalent. Functional DNA contains regulatory motifs, coding regions, enhancer-promoter interactions, splice signals, epigenetic context, and long-range dependencies. In other words, meaningful information is not merely the number of possible sequences, it is the presence of structure that does work. So the deeper question becomes, how do we distinguish structured information from randomness? This is where modern AI becomes relevant, because machine learning systems can detect predictive structure that is not obvious to human inspection. In thermodynamics, entropy counts the number of microscopic configurations compatible with a macroscopic state. If we know only temperature, pressure, and volume, There are still enormously many possible molecular arrangements. The macro state is simple, but the underlying micro state is hidden. This is why entropy can be interpreted as missing information. The crucial point is that classical microscopic laws are reversible. In principle, the full microstate contains the information needed to reconstruct the past. In practice, we never know what that microstate with infinite precision. So entropy growth becomes irreversible for us. Landau's principle strengthens the claim that information is physical. Erasing information is logically irreversible and requires heat dissipation. So information is not just an idea in our heads. It is connected to the thermodynamic behavior of matter. Chaos is not information destroyed. It is information made unrecoverable by sensitivity to initial conditions. The pendulum shows how deterministic laws can still lead to practical unpredictability. Chaos theory gives a classical example of preserved information becoming practically unrecoverable. In a chaotic system, nearby initial conditions separate exponentially. The Lupinoff exponent lambda measures that rate of separation. If lambda is greater than zero, a tiny uncertainty in the initial state grows rapidly. The system may be deterministic, but after enough time, prediction becomes impossible because our finite measurement precision is amplified. This is important for my thesis because chaos does not mean the laws have destroyed information. The equations still encode the trajectory. The problem is that the information has become operationally inaccessible. Chaos therefore gives us a bridge between thermodynamics and quantum information, the distinction between what exists in principle and what can be extracted in practice. In quantum mechanics, the state of a system is represented by a density matrix ρ, and the quantum analog of Shannon entropy is von Neumann entropy. For a pure state, entropy is zero, meaning the state is maximally specified. For a mixed state, entropy is positive, meaning we have uncertainty about the state. But the key physics point is that a closed quantum system evolves unitarily. Unitary evolution preserves information globally. The paradox is that subsystems can still look as though information has been lost. That happens because information becomes encoded non-locally in correlations. So quantum mechanics sharpens this idea that information is not necessarily local or directly observable. Information lives in relationships. Coins are only an analogy, but they capture the key move. In quantum systems, the important information may not belong to either part alone. It may live in the relationship between the parts. Suppose we have a joint quantum system AB. The full system may be in a pure state, but if we only observe subsystem A, we trace out B. The reduced state, row A, may now have entropy, even though the full system does not. Where did the information go? It is not destroyed. It is stored in the correlations between A and B. This is the formal quantum version of the thesis. Apparent loss can come from restricting the description to a subsystem. This is also closely related to decoherence, where a system becomes entangled with its environment and appears classical locally while information persists globally. Recoverable in principle, not in practice. For example, a burned book feels like destroyed information, but physically the information has dispersed into microscopic correlations among ash, heat, light, and the environment. Decoherence works similarly. Information becomes locally inaccessible because it spreads into the environment. Decoherence helps explain why quantum superpositions become unavailable to local observers. The information is not simply erased. It is spread into environmental degrees of freedom until recovering the original phase relationships becomes effectively impossible. Measurement is the most familiar place where this happens. When a quantum system is measured, it does not remain isolated. It becomes correlated with the measuring apparatus and usually with the surrounding environment as well. In textbook language, we often describe this as the collapse of the superposition into one measured outcome. The key point is that the information has not simply vanished. It has changed where it is located and how it is accessible. What was once associated with the original quantum system is now distributed across the system, the apparatus, and the environment. In that sense, measurement is another example of information becoming delocalized rather than simply destroyed. Same information is not the same meaning. DNA, for example, shows why information cannot be reduced to randomness or bit counting. Two sequences can have similar Shannon entropy, but only one may contain biological structure that performs a function. This is where the topic becomes modern and research relevant. If Shannon entropy alone cannot distinguish from random DNA from functional DNA, for example, we need methods that detect structure and function. Deep learning has become one of the most powerful approaches. Deep C used convolutional neural networks to learn regulatory sequence features from large chromatin profiling datasets. Instead of manually defining all possible regulatory motifs, the model learned patterns directly from sequence and could predict chromatin effects of single nucleotide changes. Informers went further by using transformer architecture to capture long-range interactions across roughly 100 kilobytes of DNA, improving gene expression prediction and learning enhancer-promoter relationships from sequence. These models show that information can be hidden in DNA in a way that is not obvious from base composition or local motifs alone. It is distributed across long-range structure, context, and regulatory grammar. This raises an important clarification. AI is not discovering meaning from nothing. An untrained method might notice that a sequence is non-random, but a trained model connects sequence patterns to biological outcomes because the training objective gives the model a standard of success. The loss function acts like an interpretive gate. It rewards patterns that help predict biological outcomes and downweights patterns that do not. For example, binary cross entropy might be used to predict whether a DNA region is associated with chromatin accessibility or transcription factor binding. Other models might use count-based losses for sequencing tracks or prediction error losses for gene expression. The larger point is that the loss function defines what success means biologically. So the AI does not create the information. It provides a framework for recognizing it. AlphaFold is one of the best examples of extracting hidden information from biological sequence data. The amino acid sequence of a protein is one-dimensional, but the biological function often depends upon a three-dimensional shape. For decades, determining protein structure required experimental techniques like X-ray crystallography, NMR, or cryo-EM. AlphaFold showed that a neural network could infer 3D atomic structure from sequence by using an evolutionary physical and geometric constraints. The key point for this presentation is that the structure was not created by the AI. It was already implicit in the sequence, constrained by physics and evolution. The AI provided a way to recover that hidden structure. In other words, information can be present, but inaccessible until the right model reveals it. Physics-informed machine learning makes the connection between information and physical law explicit. In ordinary machine learning, a model minimizes a data loss. Does it fit the observations? In physics-informed neural networks, the loss function includes another term that penalizes violation of a physical law, often a differential equation. For example, if the system is governed by a partial differential equation, the network must not only match data, but also satisfy the residual of that PDE. This means that the laws of physics acts as a filter. They help separate meaningful structure from arbitrary pattern fitting. In the language of this project, physical laws become a way to recognize information. They tell the model which patterns are physically admissible. That directly addresses this question: where are the laws written? In modern physics-informed learning, they are literally written into the objective function that decides which structures count as real. Gravitational wave astronomy is another example of hidden information extraction. LIGO does not see a black hole merger visually. It detects a tiny strain signal buried in noise. The original detections relied on match filtering, comparing detector data against waveform templates predicted by general relativity. That is already physics-informed signal extraction. More recently, deep learning methods have been explored to accelerate detection and parameter estimation for compact binary coalescences. The important point is not that AI replaces physics, but that the signal becomes recognizable only when interpreted through a physically meaningful model. A black hole merger leaves information in space-time itself, but without general relativity and statistical detection methods, it looks like noise. Cosmology provides another major example. Weak gravitational lensing measures subtle distortions in the shapes of distant galaxies caused by intervening mass. Because dark matter does not emit light, its information is hidden in the statistical distortion of background images. Deep learning has been used to extract cosmological parameters from weak lensing maps, especially because nonlinear small-scale structure contains information not fully captured by traditional two-point statistics. Similarly, tools like CosmoPower use neural emulators to accelerate cosmological inference by replacing expensive Boltzmann code calculations of matter and CMB power spectra. This is a profound example. The early universe and invisible matter leave information in fluctuations, correlations, and power spectra. AI helps recover that information by learning mappings that would otherwise be computationally expensive. The black hole is the extreme version of every earlier example. Information appears inaccessible, scrambled, or hidden in correlations. Holography asks whether the information is preserved somewhere unexpected, on the boundary. Black holes bring the information problem to its sharpest form. According to general relativity, information falling beyond the event horizon becomes inaccessible to outside observers. Hawking's calculation showed that black holes emit radiation that appears thermal. If a black hole evaporates completely into thermal radiation, then information about what fell in appears lost. But quantum mechanics says that closed systems should evolve unitarily, preserving information. This is the black hole information paradox. What makes this topic so powerful is that it combines all of the themes from this discussion: entropy, observability, quantum information, horizons, and inaccessible degrees of freedom. The Bekenstein-Hawking entropy formula is one of the most important equations in modern theoretical physics. It says that the entropy of a black hole is proportional to the area of its event horizon, not the volume inside it. That is astonishing. In ordinary systems, we usually expect information capacity to scale with volume, more space, more degrees of freedom. But black holes suggest that the maximum information content of a region may scale with the boundary area. This leads directly to holography. Maybe the deepest description of a region is not stored throughout the bulk, but on its boundary. This is the bridge from information preservation to boundary encoding. The holographic principle proposes that the information contained in a volume can be encoded on a lower dimensional boundary. This is not merely a metaphor. In certain theoretical frameworks, such as the ADS-CFT, a gravitational theory in a bulk spacetime is mathematically related to a quantum field theory on its boundary. I don't want to overstate this. Holography is not a proven description of our entire universe in a simple way, but it is a serious peer-reviewed idea motivated by black hole thermodynamics. For this presentation, its value is conceptual. The information we think is inside a system may be encoded somewhere else in boundary degrees of freedom. This returns to the core question. Perhaps information is preserved, but often we're looking in the wrong place. This final point is speculative, and I want to label that clearly. Established physics gives us the pieces: information theory, thermodynamic entropy, quantum information, black hole entropy, and holographic bounds. The open question is how far these principles extend cosmologically. Some speculative ideas, such as Tipler's omega point, imagine a universe contracting toward a final singularity where information and computation might become radically concentrated. Current mainstream cosmology does not require that scenario, especially because observed cosmic acceleration points away from simple recollapse. But as a speculative question, it is worth asking. If the universe ever evolved toward a more constrained boundary condition, could information become more recoverable, more compressed, or encoded in a final boundary-like state? I'm not presenting that as established physics, but as a direction that grows naturally out of the deeper question. If information is preserved, where is it ultimately written? The thread through all these examples is this. Information is not merely a number of bits. It is structure constrained by physical law. Shannon gives us uncertainty. Thermodynamics shows information hidden in microstates. Chaos shows information can be practically unrecoverable. Quantum mechanics shows information can be stored in correlations. DNA and protein folding show that function and structure can be hidden in sequence. Machine learning and physics-informed models show that new methods can recover patterns that once looked like noise. Black holes suggest that information may even be encoded on boundaries. So what we call information loss may not be destruction. It may be a limitation of access, recognition, or perspective. The universe may not be forgetting anything. We may simply be looking in the wrong place.